we're going to restrict the domain, just look at the graph from -3 to 1. Afterwards, we'll also discuss what would happen if this went on to infinity in both directions. Product rule, keep one the same, derivative of the other one, plus keep the other one the same, derivative of the other one. Set it equal to 0. You can factor an e to the x out. There's our first derivative. Now, e to the x is always positive and never equal to 0. So in this case, the only time you can get this equal to 0, this one is never 0 here, is when this part is equal to 0, and that would happen when x equals -1. Anybody factor out the 2 as well? Okay. We can do that as well. It looks nicer if the 2 factored out. Then you're left with 1 plus x. And it's even more obvious that x is equal to -1. So there's our first derivative. If we put this out, -1. Before, also never 0 and always positive. That's your graph of e to the x. So if we try a value less than -1, this second factor is going to be negative, making the whole thing negative, and after -1, it's going to be positive. So we've got decreasing, then increasing at -1. So we know that this is a local minimum. If we plug in -1, we get -2 over e, which as the decimal is negative. -7.4. So there we have our local minimum. Now going to our second derivative, I'm going to, it really doesn't matter which one you go to do your second derivative. I'm actually going to use my first one. I hope that you can see that this part here is identical to what I had to begin with. So when I do my second derivative, and I've got to do the derivative of this, and that's going to stay the same, plus my derivative of this is the derivative that I had to begin with. And I'm going to start with already, just rewrite the factored form that I had already. So now, when I factor again, I can take a 2e to the x out again. This will be 1 plus x, which will be 2 plus x. This one is always positive, never equal to 0. So x equals -2 will be my inflection point. Well, we're going to find out if it actually changes there, but yes, it will. So plugging in something less than -2 will make this negative, concave down. Larger than -2 will make it positive, concave up. So we've got -2 as an inflection point. Plugging in -2 will give me -4 over e squared. -0.54. And this is our inflection point. So So we've got our local min, we've got our inflection point. We're going to look back up here and see if we can figure out our y-intercept and x-intercept. And because I gave you a specific domain, we're also going to find out our endpoints. What happens at -3? What happens at 1? So whenever a domain is given, you'll also find your endpoints there. So x-intercept, y-intercept. Let's start off with the y-intercept. That's easiest because you just plug in 0 for x, and you get 0. Nice. That's also one of our x-intercepts. If you were trying to see if there was another x-intercept, okay? If I put in 0 for y, 2x e to the x, can split it right there. You can see that x equals 0, which we already knew was one of them. E to the x is never equal to 0 and always positive, so that would be the only x-intercept. Our endpoints, we're going to label -3 comma something and 1 comma something. Plug in 1, that'll be 2e. -3, that will be -6 over e cubed. I'm going to write both of those as decimals as well. -6 divided by e cubed, -0.30. I'll just write -0.3. And 2e is 5.44. Okay, so now we got our endpoints, we've got our y-intercept slash x-intercept, we've got our inflection point, and we've got our local minimum. Part of the reason I only wanted to give a small domain, there we go, from -3 to 1 is because it's an exponential function. It starts going up really high, really fast. Okay? So labeling our endpoints, first we had -3 comma -0.3. So that's going to be right there. And at 1, I'm going to mark that right up as high as I can here. 5.44. We know that 0, 0 was a y-intercept. We know that -1, and if this is 5.44, -1 comma -0.74 will be about there. And our only inflection point is at -2. -0.54 right there. So for our final graph, we knew this part was concave down, and after that was concave up. If we think about limits, although we stopped here, can you see that this part would keep going up? The question I have for you over here is what happens as we go to -infinity? It's going to get closer and closer to 0. In fact, there would be an asymptote at 0. To imagine that, what we have to look at is if we do look at the limit as this original function here goes to -infinity. Two things are at play. First, you have the 2x, which goes to -infinity, and you've got an e to the x, which goes to 0. Sometimes when you multiply infinity times 0, you're going to get infinity. Sometimes when you multiply 0 times infinity, you're going to get 0. It all depends what is more powerful. And in this case, an exponent is always going to be more powerful than just a linear function. It gets bigger a lot faster. So it's getting closer to 0 faster than 2 to the x is getting close to infinity. And so that's part of the reason why this function, as we go to negative infinity, gets close to 0. And it makes sense that it's going to get close to 0 from the negative side, because as we go to negative infinity, the 2x part will be a negative number. And the e to the x part will always be a positive number. So that's a little bit about what would happen, but I set it up so that we only had to graph it from -3 to 1.